Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video, we have talked about Pauli's paramagnetism, where we have seen that Pauli's susceptibility is a small positive quantity which is practically independent of the temperatures because delocalized electrons obey Fermi-Dirac statistics, and only a small fraction of delocalized electrons with energy close to the Fermi energy are able to respond to a change in the temperature or magnetic field. Also, we have seen in the band theory how the application of magnetic field splits the band, thus giving rise to an imbalance between the spin up and spin down electrons. But this imbalance is produced by application of external magnetic field. But can this imbalance be produced without the application of an external field? Which means, can we spontaneously split the bands, which will cause the material to be ferromagnetically aligned? The answer for this is given by Stoner Criterion. According to the molecular field theory, all spins feels the same identical average exchange field, lambda m, which is produced by all their neighbors. But in metals, because of the Pauli's paramagnetism, the molecular field can magnetize the electron gas. In very simple words, you can assume the localized moment in these metals to be centered at origin, and the conduction electrons are delocalized to form the Fermi gas. This localized magnetic moment creates the molecular field which can magnetize the electron gas around it. It is because of the Pauli's paramagnetism. So therefore this electron gas will get magnetized. Now the resulting magnetization of this electron gas would in turn be responsible for the molecular field. So this forms a positive feedback mechanism where the molecular field creates the magnetization and the magnetization itself creates the molecular field. We had also talked about this chicken egg scenario in our previous video of Weiss's molecular field theory. But the question arises here that can this positive feedback mechanism leads to spontaneous ferromagnetism? The answer is yes, but only under certain conditions. For that, you must have the molecular field constant lambda to be very large, and the Pauli susceptibility should also be large. It is because by having a large value of molecular field constant, you can have a large molecular field. And by having a large Pauli susceptibility, you can have a large magnetization. Now let's reframe our question. And the question that we need to ask is, can the system as a whole save energy by becoming a ferromagnet? And this answer is given by the Stoner's criteria. So first of all, let's see the band picture of the spin up and spin down electrons. Now, as we know that in the absence of magnetic field, spin up and spin down electrons are equally populated till the Fermi energy. But in order to have ferromagnetism, we must need the imbalance between spin up and spin down electrons even in the absence of magnetic field. If you see in the normal circumstances, this configuration is unstable because it is not energetically favorable state, and we are required to supply some sort of energy to create this state. But let us assume that somehow we take the small number of electrons at the Fermi surface from spin down band to the spin up band. So therefore we take the spin down electrons with energies from EF minus delta E up to EF and then flip their spins, placing them in the spin up band where they sit with the energy equal to EF plus delta E. Now in a usual sense, we can't do this. It is because this is not energetically favorable state. But let us assume that somehow we have created this situation, and we will see that in what circumstances this state can be stable. So therefore the number of electrons moved is density of state at Fermi level multiplied with delta E by 2, and these increases energy by delta E. So therefore the total energy change is given by the total number of electrons moved times the energy. So this will be the total kinetic energy change. Now this represents the energy cost in flipping the spins at magnetic field equal to 0. So therefore it looks like unfavorable, and we need some extra energy to flip the spins, but there is no external magnetic field. So what will be the source which will provide this much energy in order to have the spontaneous ferromagnetism? This extra energy is supplied by the molecular field, or what is known as the exchange interaction. It is because the interaction of the magnetization with the molecular field gives an energy reduction. It is because you must have seen the magnetic energy is given by minus m dot b. So therefore this negative sign helps in energy reduction. Here this magnetic field is the local molecular field or the exchange field. This interaction can overweigh the energy cost in flipping the spins, but only under certain conditions. To know that condition, first of all, let's write the number density of up spin and down spins. Now, assuming each electron contributes through the magnetic moment of mu b, we can get the magnetization as mu b times n up minus n down. Also, the molecular field energy, which will help in energy reduction, is given by negative of integration from 0 to m mu naught lambda m dm, where lambda m is the molecular field. So therefore the integration will give minus half mu naught lambda m square. And if you substitute equation 3 here, you will get minus half of mu naught lambda mu b square times n up minus n down whole square. Here, let's call this quantity as some u, which is a measure of the Coulomb energy. Here, in place of n up and n down, you can substitute equation 2 so that you will get the reduction in energy equal to minus half times u times density of state at Fermi level multiplied with delta E whole square. Hence, the total change in energy is given by the summation of kinetic energy change and the potential energy change. Here we can substitute equation 5 and equation 1. And the simplification will give total change in energy as half of density of state at Fermi level multiplied with delta E square times 1 minus U times G at EF. Now, as we have told you earlier that if the spontaneous splitting of energy band is stable or energetically favorable, then this total change in energy must be negative. Then only there will be spontaneous ferromagnetism. And equation 6 will imply that U times G at EF must be greater than or equal to 1. This is known as Stoner criteria. This condition for ferromagnetic instability requires that the Coulomb effects are strong and the density of state at Fermi level is large. So that if there is a spontaneous ferromagnetism, the spin up and spin down bands will split by an energy delta, which is known as exchange splitting in the absence of applied magnetic field. So that if the Stoner criteria is not satisfied, the spontaneous ferromagnetism will not occur. But there are chances that the susceptibility may change, and we can calculate the susceptibility by including the effects of applied magnetic field and the interactions. So that the total change in energy is given by where this minus MB is the term coming from the external magnetic field. Now, since the magnetization is given by mu b, n up minus n down, and if you substitute the values of n up and n down, you will get 2 mu b g at EF times delta E. So therefore, delta E is given by m divided by 2 mu b times g at EF. And you can substitute equation 10 in equation 8 so that you will get half m square divided by mu b square times g at EF 1 minus u g at EF whole thing subtracted with mb. Now for stable state, delta E must be minimized with respect to the magnetization. So therefore differentiating equation 11 with respect to magnetization will be equal to 0. And the simplification will give m divided by b equal to mu b square g at EF divided by 1 minus u times g at EF. Now the susceptibility is given by m divided by h, which will be equal to mu naught m divided by b. So this will be equal to mu naught mu b square g at EF divided by 1 minus u times g at EF. And if you remember from our previous lecture that this term is nothing but the Pauli susceptibility. So therefore the susceptibility in this case will be equal to Pauli susceptibility divided by 1 minus u times g at EF. This is the susceptibility value if the Stoner criteria is not satisfied, so that u times g at EF is less than 1, and hence the susceptibility is positive, representing the paramagnetic susceptibility. Since u times g at EF is less than 1, so this implies that chi is larger than the Pauli susceptibility, and this large value of susceptibility is expected without the presence of Coulomb interactions, and this effect is known as Stoner enhancement, and it is responsible for the enhanced polysusceptibility measured in metals such as palladium and platinum, which have enhanced polysusceptibility. Actually, these two metals are very close to be ferromagnetic, as they have a large enough value for parameter u times g at EF to cause a significant enhancement in the magnetic susceptibility, but not large enough to cause the spontaneous ferromagnetism. Now here you can see the product of U times density of states at Fermi level is plotted against the atomic number. And as the Stoner criteria suggests that this factor must be equal to or greater than 1 in order to have the spontaneous ferromagnetism. Here you can see in this graph, this factor is greater than 1 only for certain elements which are iron, cobalt, and nickel. And only for these three elements, this factor is greater than 1, so meaning that they follow Stoner's criteria and hence are elemental ferromagnets. While other 3D elements don't have enough density of state at Fermi level or their Coulomb interaction is not strong enough to make them ferromagnetic material. Here in this figure you can see the density of state of selected transition metals, which includes nickel, and here you can see that when energy is equal to Fermi energy, there is a sharp peak corresponding to the density of states. So therefore in nickel there is a large value of density of state at Fermi level. While if you see in this chromium, at the Fermi level the density of states is very low. And similar happens with titanium and other materials. But if you see here in the case of palladium and platinum, the density of state is significantly large even at the Fermi level. But still they are not ferromagnets. It is because in these materials this Stoner factor is very less than 1. So therefore in these two cases the susceptibility is enhanced by the Stoner enhancement, but since this factor is not large enough, they are not ferromagnets. Here you can see that this factor is very less than 1 for palladium. So therefore they are not ferromagnets, even though they have a large density of state at the Fermi level. These graphs are very important and these are calculated by density functional theory, also known as DFT, where using simulations you can find the density of states as a function of energy. In this theory, the ground state energy of many electron system is written as a functional of electron density, and the functional contains three contributions. First one coming from kinetic energy, second from Coulomb energy due to the electrostatic interactions between the charged particle of the system, and the last term from the exchange correlation energy that captures all the many body interactions. Here, rather than dealing with the wave function, one has to consider the electron density, and the minimization of energy functional leads to an equation which can be used to find the ground state energy, which can be plotted as shown here. The extension of density functional theory is to include the effect of spin polarization, and that is known as spin density functional theory. This technique is used to perform realistic calculation of electronic bands and to obtain quantitative informations concerning the spin density of real systems. So this is it for today, and in the next video we will start with Landau levels and Landau diamagnetism. Thank you so much for watching this video.